In this video, we're going to work through a rotations free response question for AP Physics 1. Students are investigating balancing systems using the following setup. The students have a spring scale of negligible mass that is fixed to one end of a uniform meter stick. The center of the meter stick is attached to a stand on which the meter stick can pivot. There is a hook of negligible mass fixed to the top of a block of mass m0. The hook can be attached to the meter stick through one of the small holes in the meter stick, as shown in Figure 1. The students do not have a direct way to measure the mass of the block. The block cannot be attached to the spring scale. The students are asked to take measurements that will allow the students to create a linear graph whose slope could be used to determine the mass m0 of the block. Part A. Describe an experimental procedure to collect data that would allow the students to determine m0. Include any steps necessary to reduce experimental uncertainty. Part B. Describe how the data collected in Part A could be graphed and how that graph would be analyzed to determine m0. So the idea here is that when this meter stick is balanced, then we know that the torque going counterclockwise equals the torque going clockwise. And we have enough information to calculate the torque going counterclockwise because we know the distance of the spring scale to the fulcrum and we can measure the force on the spring scale. And then knowing that, we can set that equal to the torque going clockwise. Now, the torque going clockwise will be equal to the distance from where the mass is hooked to the meter stick to the fulcrum, and then also the weight of the block. And so doing that, we can, if we know the force on the spring scale, we'll be able to calculate the mass of the block. So here are my experimental procedures. So starting with Part A, we're going to first hang the block at position 60 centimeters, and then we're going to record the distance x between the block and the fulcrum. Then we're going to pull the spring scale down until the meter stick is balanced. Then we're going to record the force F. This is the force on the spring scale. We're going to do multiple trials to reduce uncertainty. And then we're going to repeat this for the other positions, 70 centimeters, 80 centimeters, and 90 centimeters. In Part B, it says to describe how the data collected in Part A could be graphed and how that graph would be analyzed to determine m0. So first, how are we going to use that data? So one thing we're going to do is we're going to average the spring force measurements for each position. This will help to decrease uncertainty. Then we're going to plot the spring force versus the position, and this position is going to be the distance actually from where the mass is hooked to the fulcrum. And then we're going to draw a best fit line and calculate the slope. So how are we going to get the slope here, and how does that help us find the mass? So we know that torque equals RF sine theta, and in this case the R and the force is going to be, the R vector and the force is going to be 90 degrees, so sine 90 degrees is just 1. So the torque is just the R vector times the force. And the net torque is going to be 0 if the meter stick is balanced. So we can state that the torque that's going counterclockwise is equal to the torque that's going clockwise. So we have the RF on the left-hand side and the RF on the right-hand side. On the left-hand side, we have the spring force, which is 0.5 meters away from the fulcrum. On the right-hand side, we have the weight of the mass block, which is m0 g. And x is the distance that the mass block is, the distance it is from the fulcrum. And if we solve for the spring force, we get 2 m0 gx. So all I did here was I divided 0.5 on both sides, or multiply 2 on both sides. And then you'll notice that this takes on the form of y equals mx plus b. And the m, which is the slope, is equal to m0 g. And if we want to find the mass of the block, m0, we can divide 2g on both sides, and we get m0 equals slope divided by 2g. And here you can see the graph. If we graph the spring force versus x, and x once again is the distance from the mass to the fulcrum, the slope would represent 2m0 g. The students have an identical meter stick of mass m that is now attached to an axle that is fixed to a wall. The meter stick is free to rotate with negligible friction about the axle. The meter stick is suspended horizontally by a string that is connected to a spring scale of negligible mass, as shown in Figure 2. The angle theta that the string makes with the meter stick can be varied by attaching the string to one of the pegs located along the wall. The students use the spring scale to measure the tension Ft required to hold the meter stick horizontal. Table 1 shows the measured values of theta and Ft. The student correctly determines that the relationship between Ft and theta is given by And we have this equation right here, ft equals to 5 mg divided by 6 sine theta. The students create a graph with 1 over sine theta plotted on the horizontal axis. So here you can see that I've already calculated 1 over sine theta. This gives us a hint that we're probably going to use this. So make sure when you do that you are in degree mode. Part C, indicate what measured or calculated quantity could be plotted on the vertical axis to yield a linear graph whose slope can be used to calculate an experimental value for the mass m of the meter stick. So what we're going to do here first is try to make this equation look like y equals mx plus b. So if we factor out the 1 over sine theta, which the problem already told us that's going to be on the horizontal axis, so that's going to be represented by the x here. Then what's left over here is going to be the slope. So 5 mg over 6, that is the slope. And then if you wanted to find the mass, we would just isolate the mass, and we would get 6 times the slope divided by 5g. Part 2i, on the blank grid provided, create a graph of the quantities indicated in Part ci that can be used to determine m. Use Table 2 to record the data points or calculated quantities that you will plot. Clearly label the vertical axis, including units as appropriate. Plot the points you recorded in Table 2. So here is the graph that I graphed using the data points from up here, from this table right here. So I'm plotting 1 over sine theta on the x-axis and then ft on the y-axis. And notice that for the best fit, I drew a best fit line, and notice that the best fit line is a straight line and is as close to as many dots as possible. But also notice that the 2 points that I pick to calculate the slope are not the data points. And so you want to be careful with that, because oftentimes the data points are not on that line. So you want to make sure to pick 2 points that are on the best fit line. And then we're going to use, for the slope, we're going to use y2 minus y1 divided by x2 minus x1. You could also use rise over run as long as you do it correctly. Then we're going to substitute the coordinates into the x and the y, and then we solve for the, evaluate this, and we get 8.1 newtons. 3i states, draw a straight best fit line for the data graphed in part C2i. And we did draw that best fit line. Part D, using the best fit line that you drew in part C3i, calculate an experimental value for the mass m of the meter stick. So this was the equation that was given. We did rearrange it to make it look like the y equals mx plus b equation. The slope is equal to 5 mg over 6, and we're looking for the mass. So if we isolate the mass, we get 6 times the slope divided by 5g, and the slope is that we calculated up here was 8.1, so we're going to substitute 8.1 here for the slope, and when we calculate this value here, we get 0.99 kilograms.